Okay, so what I want to do today is discuss one further property of TC, also a non-trivial computation, and I'm going to do this in order to bring and motivate the use of a standard technique in homotopy theory, namely obstruction theory. So let me start by introducing the actors. So at the beginning of these lectures, I already said that a space has topological complexity 0 if and only if this is contractible. So what about understanding the meaning of having a space of topological complexity 1? Well, for instance, it is a standard that if X is a co-H space, well, the category, the Luster-Schneiderman category of X is at most 1. And it would be 1 if it is not contractible. So, in fact, Whitehead proved that spaces having category 1 are just co-H spaces. So, X is a co-H space if and only if it has category 1. So, well, the question is, can you give some sort of a similar result, but instead of using category, just use this relative TZ? Well, and the result was proven by Mark Grant, Gregory Lupton, and John Oprea. And they show that, well, at least if I restrict myself to working on spaces which have this homotopy type of a finite type CW complex, then TC of X is 1 if and only if X has a homotopy type of an odd sphere. Of course, we know that odd spheres have TC1, but actually those are the only cases. So in particular, well, notice that if you have a co-H space, namely something that has category 1, for instance, so e.g., if X is a co-H space, well, we know that the category is 1, but we know that the topological complexity is bounded from above by twice the category. So the topological complexity, then, topological complexity of X, which is at most 2 times the category, would be at most 2. And by the theorem of these guys, then we know what happens. Namely, co-H spaces have TZ being 0 if and only if they are contractible. Have TZ1 if and only if they are actually a suspension and they are actually an odd sphere. And they have TZ equals 2 in any other case. So what I want to discuss today, one of the things is the proof, the ideas behind. This is quite easy if one assumes that X is simply connected. But if it is not, if you have a fundamental group, then you have to actually do a little bit more of work to prove this result. Good. So here's for the proof of that, this is based on 2 results, which are rather easy. Namely, suppose that the topological complexity of a space is 1. Well, what can you say? Then the cohomology, you could look at the cohomology of X with coefficients in a field, any field, in case is a field, and look at the reduced cohomology. So this is a graded vector space over K. And I claim that you can prove that the dimension over K as a graded vector space is at most 1. Notice that I'm already removing the 1 on the bottom. And suppose here X is connected. So, well, this is sort of very elementary. Let me just give the reason. Suppose you have two elements in the cohomology of X with coefficients in K, which are linearly independent. Well, then this is very simple. You could take the following zero divisor. This lies in the cohomology of X times X, and multiply it by B times 1 minus 1 times B. And when you do this multiplication, notice that these two guys are 0 because, well, this is a bound for the category of X so that it is an co-H space and there are no products in co-H spaces. So these two guys will be multiplying trivially, and what is left is basically up to signs is A tensor B and B tensor A, and those are just part of basis because these are linearly independent. So, all right, so we have this thing. Now, it's let me put this as an exercise. I think that's exercise. Thank you. Thanks. So, an easy proof, an easy application of the universal coefficient theorem, so this is a standard exercise, tells you that this hypothesis, if the dimension of the cohomology of X is at most 1 for every field, okay, then there are either one of the following two things happen. Either X is acyclic, meaning that the homology, the reduced homology is trivial, homology doesn't see anything, or it is an integral homology sphere, or X is a sphere homology. Namely, it has only two non-vanishing homology groups, the bottom dimension and in some dimension error. Furthermore, if actually TC of X is 1, so that this hypothesis then holds, then in fact R must be, well, if TCX is in fact 1, then R is odd in the second possibility. Okay, so let me use these two things to prove this result in the elementary case. Of the Grand Lupton opera result. So let's see, what can I do? So I'm assuming that TC is 1. All right, then notice that, and I'll do it with the assumption that X is trivial. Sorry, let me just do the first, this simple case. Okay, if the fundamental group is 0, then X cannot be acyclic by the Whitehead theorem. Has no homology, has no homotopy, fundamental group, so it has to be contractible. So, but that is not possible because we're assuming that this is 1. So, X is a homology sphere, an integral homology sphere, for some odd number R. Well, notice then that what is the pi r of x, it has to be, by the Hurewicz theorem, x has to be r minus 1 connected, and the first non-trivial homotopy group that you see is the first homology group that you see, which lies in dimension r, and this is z. So you can take a generator, take a map into x, which is just, say, this generator, and notice that this is, again, an isomorphism homology. Namely, this is a homology sphere. This is an isomorphism in these homotopy groups, which is the same as in homology. And this has that homology of that, so it's an isomorphism in all possible dimensions. So this is actually a homotopy equivalence because X does not have a fundamental group. Okay, good. But things get a little bit more complicated when you have a non-trivial fundamental group. And so let me introduce, let me recall most likely some standard techniques in algebraic topology. So let me talk about cohomology with twisted coefficients. I have a non-trivial fundamental group. So suppose now that from now on, pi will be just the fundamental group of some space and, well, would not be a trivial group. And I will also look at the universal cover of X. So recall that if you have a pi module, M, a pi module, well, you can form the following. There are two standard ways of defining cohomology with twisted coefficients. So what you could do is take the chains on the cover, on the universal cover. Notice that pi acts on here as the covering transformation deck. And so that gives you an action on the chains. And now you could take the homomorphisms into the module. So that gives you, for you, a cochain complex, and you could take the cohomology of that thing. And recall that this is, by definition, the cohomology of X with twisted coefficients. You're taking into account the way that the fundamental group of X is acting on M. All right, so with this information, let me define a nice element. Namely, this is called the Bernstein-Schwarz class. Let me call it BS. And this is defined as follows. Well, you could do the standard construction of taking the group ring for pi, take the augmentation, and look at the kernel. Let me denote it by IP. So this is a short exact sequence of pi modules. And it leads to a long exact sequence in cohomology with twisted coefficients. So you could look at the cohomology in dimension 0 of pi, or the classifying space of pi, with coefficients in, what do I want to do? In Z. So this is a copy of Z. And I'll take the connecting homomorphism, which goes into the cohomology of B pi with coefficients on this module. And notice that this is just a copy of Z. So you could take here, you could take here 1, the generator, and just look at the image under this connecting homomorphism. By definition, that guy is the Bernstein-Schwarz class of the group. So let me denote it by BP, B pi. So this is the Bernstein-Schwarz class. All right. Well, notice that this has some basic properties. Namely, if the group pi has m elements, and here m could be infinite, then this class has order also m. Namely, m times that is 0. This is quite easy if you look at not the previous map to the connecting homomorphisms. So you look at cohomology in dimension 0, and that's just the invariance. And invariance in here, you would only see invariance if this is a finite group. And the only invariant would be the sum of the elements. And that under the augmentation is mapping to the number of elements. And so that gives you, if you think a little bit, this fact. All right. In particular, this guy is non-zero, if I'm assuming that the group is not trivial. The other property is it has a beautiful property of universality. Notice that this class, it can be defined in purely algebraic terms. Just take the group, not the classifying space, and take the cohomology of the group, compute everything just in group theoretical terms. Now, well, the property is the following. For any class alpha in the cohomology, say in dimension k, of our group with coefficients in some pi module m, there is a morphism of pi modules from the k-fold tensor product of this kernel into M, so that in cohomology, sorry.
Oh yeah. In what sense are we taking the degree of this class? No, yeah, that.
Oh, that just means that this is an element in some group, and that M, in the sense of groups.
Order.
Order.
Oh.
The how many times you have to add itself so that you get 0. So for any class in the cohomology of the group, absolutely any class, there is a morphism so that if you think of this class, not in M, in the cohomology of the group with coefficients in M, then it comes from when you take this. This is about. Sorry. So that this map induces a morphism in cohomology in dimension 1 from pi with coefficients here into here and to here. You have here alpha, but then you have here the fundamental class take its kth power, which has its product, its cup product has coefficients in this module, and it hits this guy. So absolutely any cohomology class comes after changing the group, the module, the coefficients, from a suitable power of the Bernstein-Schwarz class. That's nice. The other thing is, and again, this is group theoretical stuff, so it's actually quite manageable. So it is natural. Well, what it doesn't mean to be natural, I have only defined one element. Namely, I want to do it the other way around. Namely, suppose that X is a space with fundamental group pi. Then, well, you can take the classifying map into B pi of the universal cover. All right? And you can look at what happens in cohomology. You have cohomology, and let me take the dimension 1 of pi, B pi, with coefficients in I pi. And I've defined here a class beta p, and these maps This restricts under these maps into the cohomology of X with coefficients in the same thing. This is an I. And by definition, the image here would be the Bernstein-Schwarz class of this space, which has fundamental group pi, beta X. So that's a bunch of properties. I'm not going to say, but again, this is just group theoretical, verifiable. Now, one nice exercise is that, now I understand why I never learned how to write exercise. Is that if you look at that situation, then for every pi module m, you could take the induced map U H2 b pi m. And I claim that this map is a monomorphism. Noticing that in dimension 1 I have a good control that this Schwarz class goes into the Schwarz class. But what happens in dimension 2 is that this is just part of that. This is monic, a monomorphism. So that's an interesting example, exercise. And I need finally one extra ingredient for these purposes. So here's a theorem, and this is a deep theorem. So I'm not going to say I didn't say any things about easy things, but I'm not going to say either things about this more deep result. This is a theorem of Stallings and Swan that says that free groups can be characterized in terms of their cohomological dimension. So it says that free groups are characterized by having a cohomological dimension 1. So free groups are really large things, but cohomologically they are very small things. So let me just recall for you what this number is, the cohomological dimension of a group. So essentially you have to see what's the largest possible dimension in cohomology with any coefficients that pi can see. So here, CD, the cohomological dimension, definition of a group is just the maximal K, so that you have some pi module M, so that the cohomology of pi with coefficients in M is non-zero. It's the largest possible cohomological dimension with any possible coefficient. Notice that you can also define this because of the universality property. If you want to see elements in any module, well, you can just always use this as M. So this is the maximal K, so that when you replace coefficients, you can use I pi to the K being non-zero. And even more, it's explicitly, namely, these elements is everything up to changing coefficients. So it's just the height of that element. This is the maximal. This is the same thing. So that, yeah, well, here you have to remove that. That's the whole point, that you don't need any module. This is the maximal K, so that this is non-zero. And here you have the maximal of the case, so that this class is non-zero. Notice that from here, it is clear that this number is less than or equal to the category. Note. Cohomological dimension of pi is less than or equal to the category of b pi, of b pi. Because, say this number is k, so this product is non-zero. There you go. You have a product. But these are results that I mentioned at the beginning in the first lecture. So you have this, actually this inequality. And in fact, there is an equality. It is a nice fact that the category of the group defined as the category of B pi, is just the cohomological dimension of pi. And this is something very nice. You have a homotopical invariant of this space, B pi, the category, that invariant, which is determined, which can be computed, can be determined in purely group theoretical terms as a cohomological dimension. So, question.
But does it say much, right? Because the cohomological dimension, when it's finite, is infinite, right?
It could be, sure. Oh, yeah. No, free groups.
Well, when it's finite.
Yeah, sure. But in the case, also free groups is elementary, but that's another situation. A question. So this was proposed by Michael Farber, and then you can write this in your notes of open questions that you could possibly try to think of. Namely, the task is compute the topological complexity of the group, finite, infinite, whatever group, just abelian, non-abelian, in terms of group theoretical information of the group. Namely, let me define this as the topological complexity of the classifying space, and this is what? As a functor, as something that depends only on the group, not on the space. Okay, well, back to what I want to do then. Sorry, say that. This is something that I'm asking for. I don't know what's the answer. What's the answer in terms of group theoretical terms, depending on the group, so that give the topological complexity of this classifying space. An example would be orientable surfaces with a large fundamental group, but we know what that is. I told you what the topological complexity is of orientable surfaces. Okay, now. So the key ingredient for the proof of this theorem of Grant and et al. About TC being 1 is the following. Notice that if the category of X is at most 1, then, and this is a standard fact in, for instance, in low-dimensional topology, that the fundamental group of X is free. So it's quite restrictive. And the reason for this is that if it is not free, then because of this result, you have large cohomological dimension. If it is not free, it has cohomological dimension greater than or equal to 2. And so therefore you have some power, some product which is non-trivial. And that gives you a large category. In other words, I prove the converse. The contrapositive, I guess. And okay, good. So here's a proof. Here's the sketch. Well, it's the idea. but it's not complete. There is one subtle point that you had actually work a little bit, but it's a nice application of the ideas that about the Whitehead's theorem, how much you can actually, it is true in other contexts. So let's see. So suppose Tc of x is 1, and now I have a non-trivial fundamental group. Of course, this is greater than or equal to than the category, and the key ingredient then tells me that if the category is at most 1, then the group has to be free. And the category being at most 1, then this has to be free. Not only non-trivial, but it has to be free. So let's see. Pi 1 of x is free. Now, using the exercise and the first lemma that I wrote, you can see then that x has, because it has Tz being 1, it has to be a integral homology sphere. So, and x is integrally a sphere. If you look at what happens in homology, you would see that R has to be 1. I guess. Right, because otherwise, what is that? R has to be 1, and fundamental group of x has to be this free. Let me see why. I'm not seeing. Well, let me just leave it as an exercise. This is supposed to be elementary, but I'm just being here, I'm just kind of blind. But this follows by elementary reasons from what I said. So you can check that this is R, and the fundamental group is what is Z. Notice that the homology has to be the abelianization. The fundamental group was free, and the homology has to be the abelianization. So it's free abelian, some rank, but I said that is the same rank of the free group, and I said it's a homology sphere of a circle. So it has to be free of rank 1. So that's basically the reason for this part. And this is just supposed to be simple. Good, what can I do with this now? The punchline is that then you can do the same thing. Take just a generator from S1 into X. And what does this have? What properties does this have? Namely, this is a pi 1 iso, just because I choose it so. It is also an homology iso, because X is a homology sphere, and what you're seeing in homotopy group in pi 1, then you just also see it in H1. So this is an H homology iso. And when can I conclude that this is a homotopy equivalence? Well, if Whitehead's theorem is true, at least the homological version, then you would say that this is a homotopy equivalence. But, however, this is not in general. This theorem in this generality actually fails. But Whitehead, so S1 is homotopy equivalent to X if X is a space where this intended generalization of the Whitehead theorem applies. For instance, if even if you have a non-trivial fundamental group, but if it is abelian, or more generally, if the space is simple, then it's well known that Whitehead's theorem applies. Or nilpotent. The space is nilpotent. Namely, you have an nilpotent fundamental group acting nilpotent in the higher homotopy groups of the space. Then Whitehead's theorem holds. But otherwise, it might be false. So here's an interesting, so this is the proof. Well, no, the proof is, what do you do if the space is nilpotent? Well, what you do know is this extra ingredient, namely that since the topological complexity is 1, the category of X is at most 1, And so it is a co-H space structure. It is a co-H space. And on those conditions, the conclusion of the Whitehead theorem applies. And this is a homotopy equivalence. So you have to use, in addition, the co-H space structure. And a result, this is a result of Iwase and two other guys under the name of Saito and Sumi, which I can tell you the explicit reference if you ask me. Okay, so that's the idea. So it's still standard homotopy theory, characterizing spaces with TZ1. But let me, now that I introduce the Bernstein-Schwarz class, well, this is a baby example. Well, this is a kind of a special situation of obstruction theory. So the Bernstein-Schwarz class is a specialization of obstruction theory in homotopy. So let me, namely, you have the classifying space. I defined here in the cohomology of this a class. And you have, of course, this vibration, which is this contractible. And since I already said that, notice that this has a section, if and only, since it is contractible, if and only if this BP is contractible, B pi is contractible. And, well, the group is being trivial. So essentially, the Bernstein class is the first and unique, is the fundamental class for finding a section for this. In obstruction theory, the obstructions, as I'm going to try to explain next, lie in the cohomology of that with coefficients in the fiber. And there is only one such. In the coefficients of the homotopy of the fiber, and there is one such homotopy group. Okay, so let me use this. So here's an exercise, by the way, of how the conclusion here may fail if the space has a sort of a crazy structure, but really not that crazy because it's even a CW complex. So the exercise is consider the wedge. This is an exercise in Hatcher's book. So consider the wedge of a circle and a sphere. I'm going to define a map into this wedge, and let me consider the cone. So let me attach a cell of dimension n+1 via this map. Well, notice that the cell structure here is quite clear. You have a cell in dimension 0, the base point, cell in dimension 1, cell in dimension n, and a cell in dimension n+1. So now take, I haven't defined this map, but I will. Take the inclusion of the one skeleton. And the exercise is, once I define this, is that proof that this inclusion satisfies those conditions and is not a homotopy equivalence. Namely, this inclusion, I, is a homology iso. It's an isomorphism in fundamental group. Even it's a P star iso up to dimension n. However, it's not a pi n iso. It is not. It is not an iso in that degree. So cannot be homotopy equivalence. So this space is really crazy. So let me define the this map alpha. So notice that the universal cover of this wedge, so the hint, and even the definition of the map, notice that the universal cover of this, well, you have to unravel the circle, but the sphere is already unraveled. This n is supposed to be large. So this looks like this. It's a copy of the reals, and over each integral integer number, you put a sphere of dimension n. So that's the universal cover. So if I want to look at pi n, I want to find an element here, so I have to look at pi n of this thing, which is the same thing as pi n of that. And then notice that this has the homotopy type of a wedge of Sn's, as many as z, and then the map is easy to see. Alpha, in these terms, defined through the lifting of the universal cover, is the map sending a Sn into the wedge of these guys, so that it grabs twice around say, the sphere over the one. It grabs twice here, and once in the opposite orientation around 0. So that simple trick does it, and you can then prove these sort of things. All right. But now let me go into the second part of the talk. And I am doing regularly that, and that. So the goal now is use obstruction theory, motivated by this use of the Bernstein-Schwarz class, to compute the topological complexity of the configuration space of a Euclidean space with n distinct, pairwise distinct points. Let me just try to tell you this problem. So suppose you're in the neighborhood of an airport, and all of a sudden n planes show up in the radar, in some Euclidean neighborhood of the radar. And then your task, being in the control tower, is that you have to organize the movement of these planes from one given position into one given position. Of course, this has to be done without having collisions of these guys. And the final position may be just parking the planes just on the gate that you're supposed to board. And so, well, the configuration space of this system is nothing but the configuration space of n planes. This is just a model, particles, n distinct particles in R3, in some Euclidean neighborhood of the airport. So the question is, well, what's the minimal number of instructions that a manual has to have in order to organize these procedures? Any position that the planes come and they have to arrive in certain position, this is supposed to be done through certain instructions. And what is the minimal number of this booklet that has the instructions? So in other words, what's the topological complexity of this thing? So let me just compute, in general, this configuration space. It would be elementary in the case that M is, I don't remember if it is even or odd, and it would have to use obstruction theory in the other cases. So let me start defining what I need. So let me define the fiber-wise joint product of fibrations. So this is a standard construction. Suppose you have fibrations with a common base space E2. We all know what it is the join of two spaces, namely you just have to take lines between points of these guys. But I want to do the same thing here, but I will only be joining points that lie in fibers, in common fibers, in fibers over the same point. So the E1 join over B or with E2, and I will actually be defining a fibration P1 join over P with P2. But let me define first this space. Well, this is just the fiber-wise joint product of the two fibrations. Namely, you can think of this as being the co-whisper map in the homotopy push-out of the pullback of the two fibrations. So what this amounts to saying is this. This consists of the points x1, t, and x2 in E1 cross the interval cross E2. Now, I should think of this as being, this is a line. This is the ratio of this point in the line joining these two guys. These two guys are supposed to be in the same fiber, so that P1 of X1 is P2 of X2. So they are in the same, in the fibers over the same point. And then you have to mod out by certain relations that just are saying that this is real, these are actual lines. Namely, you have to mod out by the fact that if you have x1, 0, x2, and this is just the beginning of the line between x1 and x2, then if you change the endpoint, it doesn't have to change. This is equivalent to x1, 0, and x2 prime. And if you're at the end of one of these lines, this has to be identified. This is a 2. So this is the end of this line. So this is supposed to be the point that really matters. So this is x1 prime, 1, x2, for any such guys. You have to make those identifications. And I already defined the space. And there is a map from this space, which I'm going to define in this. And this is the map that goes into B. And it's just sending this, the class represented by this into either P1 of X1 or P2 of X2. It's just, so you're just taking fiber-wise joins. Okay, now you can iterate this construction. So if you have n plus 1, any number, P1, Pi from EI into B, you can do just the same thing, that just replace lines by simplices, and simplices if there are n plus 1 guys. And do the same thing, just put a simplex between, with vertices, the points on common fibers. And do the same thing, they do the corresponding things. So you can define the join fiber-wise product of the PIs from a space, well, you could call it that way, into B. Just doing the same thing, the natural thing. All right. Now, in particular, I want to look at a power, join fiber-wise powers of a single fibration. So the definition is, that's it. Oh, here it is. In particular, for a fibration P, Jn of, it's supposed to be a little lower case, J, P, going into capital J, N, P into B. This is just take P, take your fibration P from E into B, and multiply it in this way, fiber-wise, with itself as many times as n plus 1 times. So this is the join fiber-wise join product power of P with itself n plus 1 times. This is just a matter of taste, what you prefer to do. I prefer to normalize category, sectional category, just by counting one less than the number of, well, but this is that's the same. I don't know what I said. Okay, now notice that you have the situation. A nice property of these things is the following. Note that you have E1 down into B, so this maps into B, and here you have here E1 into B, and this sits inside the lines at the beginning of each line with parameter 0. So in general, this holds, and notice that J0 of P mapping down into B by J0 of P, which is nothing by E and P. This sits inside a phase of these powers. J1P, and this is sits inside as a one-dimensional phase of the triple product, and so on. J2 of P, and so on. So you have here J1P, you have here J2P, and so on. Now notice, what is a fiber? I didn't tell you, but this is a fibration. If you start with a fibration, if you start with the product of many fibrations, this map is a fibration. And what's the inverse image of a point? The fiber, well, it's just the join, the usual join of the fibers. Because after all, you were doing the join construction fiber-wise. And if I just restrict to what is happening over a single point, fixed point, you're just taking the join. So notice that the joins of these guys are the joins of the fibers of P. And if I iterate this, then the fibers, as I think Jose mentioned, the fibers become more and more connective. And so these guys become more and more like equalities, like identities, homotopy equivalences. So, okay, notice that this thing tells you, in particular, that the sectional category of P, so what should happen to the sectional category of something that is more and more like an identity? What is the sectional category of the identity? Well, it has a section, a global section, so the category just decreases. And that is what is happening here. So the sectional category of this is greater than or equal to the sectional category of J1, this is J0, and so on. And the question is where do these numbers stabilize? They are all positive, not negative. In fact, a result, which should be an exercise, is not that difficult to prove, is that the sectional category of J and P equals the integral part of the sectional category of P divided by n plus 1. That's a nice result. This is just followed by understanding a little bit of the geometry of these simplexes that you're using to glue fibers all together. All right. So, in particular, I want this property. Corollary is that the sectional category of my fibration is at most n if and only if this guy is 0. If this sequence already stabilizes at the nth point, J and P. So this fiber n plus 1 times iterated fiber-wise joint product of P already has a section. So what's the moral here? Well, this says that the multiple sectioning problem for a fibration is equivalent to a monosectioning problem. And of course, you can use obstruction theory to understand this monosectioning problem. So that's the whole point. So example, I guess, yeah, example. So suppose you have a fibration and suppose that B has the homotopy type, the homotopy dimension of B is D, has the homotopy type of a CW complex of dimension D. So this is a CW complex with dimension, say, D. And suppose that the fiber starts, the homotopy groups of the fiber start in dimension S. So suppose this is S minus 1 connective. F is S minus 1 connected. Then the sectional category of this vibration is at most, just for free, at most the dimension of the base divided by s plus 1. Now, the way to prove this, I'm not going to, I was supposed to go into detail, but I might not have enough time. But the idea, what you do? Well, you want to say, call this number q. Well, of course, this is a non-integral number, so you have to take the quotient of this divided by this and forget about the residue. So you want to say that this is small. And using this thing, you want to say that certain power of this iterated joint product is 0. The sectional category is 0. But the point is that if this number is high enough, then this would be a vibration with a highly connected fiber. And the obstructions, I will tell you a little bit about the yoga of the obstructions, lie in the cohomology of the base with coefficients, perhaps twisted, in the homotopic groups of the fiber. But the homotopic groups of the fiber are supposed to be larger than the dimension of the base. So there is no way you can get a non-trivial group. So there are no obstructions for sectioning the relevant power, fiber-wise joint power. So that's the idea for this. And this is a good exercise. So by the way, you should be taking notes of that because those are the examples, the exercises for the session problem. Good. In particular, if you apply this to x times x, the double evaluation map, whose fiber is the loops on x, this is an evaluation, and the fiber of over a point on the diagonal is clearly the loops on that point, well, you immediately get that the topological complexity of a space is at most twice the dimension of the space, say the homotopic dimension of the space, divided by where the homotopic groups of x start. Here x is s minus 1 connected. So this is a nice, very useful upper bound for TC. It depends on, if you don't want to deal with obstructions, you want to get things for free, just look at the dimension of the base and look at where these homotopic groups of x start. Notice the shift in dimension because the fiber is just one below. And that gives you for free. But now the interesting thing is when you are in situations where obstructions, possible obstructions, can actually appear. Good. And this example of the configuration spaces is a nice example of such a thing. This is work, so I'm going to be describing work by Michael Farber and Sergei Yuzvinsky and Mark Grant, and I think that those are the guys involved. Okay, so I need a little bit of homotopical input. So recall, the goal is to understand the TC of configuration spaces. So I'm using interchangeably F or conf for configuration spaces, depending on if I'm in a hurry or not, of configuration spaces of Euclidean spaces, say M with endpoints. Okay. So I need a little bit of homological input. Good. So what's the cohomology? This is a theorem, but for me it's a lemma. What's the cohomology of this configuration space? Well, this is classical. Many people involved here. Several points of view. But let's see. There are classes. The cohomology of this is polynomial with certain generators subject to just one single type of relations. Now the generators arise as follows. So suppose you have this guy. Let me map this into a sphere. I want to define spherical cohomology classes into n minus 1. How can I possibly map this configuration space? Well, suppose that you have an element here So n tuple of elements in Rm. And then let me just fix I and j in this range, 1 to n. Different guys. Suppose I is greater than j. Okay, now take those two. They are different, and take just the difference, the difference vector normalized. So this goes to the normalization of xi minus xj. So that defines for me a map. And of course, I can fix a generator and look at the image here. And let me define this as, it depends on your preferences, but I use this notation, A, I, J. So these are elements of dimension n minus 1. They are spherical, their squares are trivial. And the lemma is that it's not very difficult to see that these are generators of this ring, of the cohomology of this ring, for any coefficients, actually, for any ring of coefficients, any ring of coefficients. These guys generate this algebra. So this, sorry about the mess, but the point is that the cohomology of this is polynomial. So let me use just integral coefficients, but this is valid for any coefficients. On these classes, subject only to a nice three-term relation with nice relations to other areas. So suppose you want to multiply aij with aik. Suppose a is greater than j is greater than k. So notice that it is the same first index. Well, this is just the difference times ajk. You have to work a little bit, but it's not terribly awful to prove such these relations. And this is you have to divide by the ideal generated by these guys. Notice that in this ring there is no torsion. The only thing that these relations are doing is that whenever you have a monomial with two i's that share a's, that share the same first index, you just replace them. So think of this as being inequality. You just replace them by another difference of monomials in which you have gone in the second first index lower. I don't know if that's well said, but essentially this guy is less than that and less than that. So this is the only kind of replacement that you're doing, right? So essentially, if you work this, just iterate it in an iterated way, you will see that there is no torsion and a basis which has basis given by the order monomials. Namely, you have to take A1, J1 up to A, I, R, J, R, so that I1 is greater than so on up to I, R. So that's set of generators. That's, you have to look at that thing as a basis. Sorry, I said a basis for this thing. Good. In particular, notice two nice things. Notice that this description suggests that these spaces are simply connected. Indeed, their homotopic groups are starting in the dimension of the generators. n-1. It's not difficult to see that at least that they are these spaces by some nice vibrations, Fadel-Neuwirth vibrations, that these spaces are simply connected. And then you can construct, by a cellular approximation, you can construct a model for it, taking for each generator in the cohomology, or dually in the homology, take a generator, and then you just, by a Whitehead's theorem, there is no problem with the fundamental group, you have a model for these spaces. Corollary 1 is that these configuration spaces have the homotopy type of a cellular complex whose bottom cells start in dimension n-1, that's the dimension of the generators.
Yes, so this has basis, you know, AJ1 to JR. What is R here?
Any R. R goes from all possible R's. So subject to this relation. This is.
Okay, all right.
So for the crux of the matter is that R goes from 2 up to, and this is a good point for what I have to say, to N. So notice that I, this is this guy, goes from, it cannot be 1 because it needs a lower index here. It goes from 2 to N. So the largest possible R is in between this range. And the largest possible basis element, which is a product, has length n minus 1. And that's the top dimension in the cellular approximation. So that's precisely the top dimension. This is the length of the monomials which have this degree. And this is the cell that you have to attach to realize that guy. Okay, this has the homotopy. So it's nicely connective, and we know the homotopy dimension. So we know then, in particular, that, I'm going to skip that, that the topological complexity, well, no, let's just say it. This is an interesting comparison. The category of this guy, because of these kind of situations, is bounded from above by the dimension, not twice the dimension, because the base is x, not x times x for the evaluation maps. Is at most given by the dimension of this guy, the homotopy dimension, which is that, divided by where this, the first homotopy group appears. And that appears in dimension n minus 1. So this is n minus 1. And a lower bound is given by the cup length. And I already told you that you have a maximal product here, which has length n minus 1. So this is n minus 1. Category of that. So you compute that. The category of these guys is well known. This is a paper by a guy, the master's thesis of a German, Fridolin Roch. In other ways, using other techniques. So you can compute that. However, topological complexity of these spaces, you can do the same thing. The upper bound is given by, well, now you want twice the dimension, and you will get 2n minus 2. And it is less than or equal to some bound given by the length of 0 divisors. And so the next ingredient is again cohomological. So I mentioned this because the answer here, the answer for the category is just given by this simple argument, but in this case, the answer will be, I'm going to show that, well, the point is that just by looking at product of 0 divisors, you can just see that this is a lower bound. And then you can see, I have to speed up, so I might retake this the next time, but let me just now try to close this up. The point here is that there is a product of this length in the cohomology of 0 divisors, which is non-zero. The product is non-zero. So you for free get this inequality. And moreover, when, I have to see, when m is odd, you can improve this to 2n minus 2 if n is odd. And that does it. But when n is even, this dimension, it is independent of the number of points. But when m is even, it turns out that the answer is this guy. And so you have to actually produce either an explicit motion planning, which by the way is almost known, or by this work of Hugo Mas with Enrique, or improve this upper bound. And recall that the point here is that, recall that this upper bound is given for free just because there are no obstructions. If you want to understand what happens if, you want to understand what happens for this possibility of this configuration space being at most 2n minus 3. Now, if you do numbers, if you do math, you will find out there is one obstruction, the top one, but also the bottom one, in the sense that it's the only one obstruction. Connectivity of the fiber of this guy and the dimension just allows one possible obstruction, and that is called the fundamental obstruction, the first one. In general, when you do obstruction theory, you have to deal with indeterminacies of these guys, which is I was supposed to explain. I might do it next time. But when you find the first obstruction, there is no indeterminacy. That's just called the fundamental obstruction. And the thing is that you can prove that that fundamental obstruction is a product of zero divisors of a length that you already know that any product of such length of zero divisors is 0. So the obstruction is trivial. But you have to do some explicit computations. But at the end, as people say, by obstruction theory, you prove that this is the answer when m is even. Okay, thank you very much.